Hello everyone. Uh, in the last lecture, we learned about uh, the kinetic theory of gases and how it talked about how it could pave the way, or it rather paved the way for later models to explain the conductivity or the resistivity of metal. And we also talked about how in solids the specificity is different compared to a gas collection of gas molecules. And we also talked about the equipartition theorem, and we also talked about the Maxwell-Boltzmann distribution. And I emphasize at every point that learning the kinetic theory and the kinetic theory will be very much helpful as we proceed on with our next lectures, when we go on to learn how conductivity and resistivity arises in a metal. So let me recall some points or important points of the kinetic theory where we recap of kinetic. So we considered in a container let's check whether it is recording or not. Yeah, it's recording. So we talked about that in a container, the gas molecules are there. And they're moving completely random. The motion is randomized. In the process of randomly moving, they collide with the walls of the container and also among themselves. All right. And the collisions are perfectly elastic. There's no energy transfer between them, so that there's only kinetic energy, and the particles, and most importantly, the particles are non-interacting. So there's no potential energy and only kinetic energy. All right. Now, what happens that in between collisions, the particles move in a straight line and with a uniform velocity. The moment they collide with one another, the time is very small compared to the time between collisions, and the motion is completely random. All right. So, and the most important thing in this to talk about is that they're non-interacting. There's no potential energy. All right. There's the highlight. So, as the motion is random, the net average momentum of the particles, that becomes, naturally you can assume that that's zero, because the motion is completely random. Okay, so this we talked about in the last lecture. But when we transition into a solid, as we already said, that there are positive ion cores and there are negatively charged electrons. In gases, we only talk about one kind of particle, and that is the gas molecules. All right, there's no other ion cores or something to talk about. All right, but you see that if there's electrons in a solid, then we know that the solid, the metal is neutral. So something has to be there which has to nullify the charge or the negative charge of the electron. Where from does that come? That comes from the positive ion cores. So when atoms are brought together, when in a metallic system, when atoms are brought together to form a metal, they the valence electrons, they randomly move around. Okay. So let me just write down what I'm just saying. So for solids, metal in particular. So the picture is like this, very familiar picture. The positive ion cores are there. There are positive ion cores. There are draw few. And the electrons, the valence electrons, they move around randomly. They are negative charges. The electrons, they have negative charges. All right. So in a metal, the valence electrons move about randomly, and there are the positive ion cores. They have very high mobility. They are able to move the electrons, but the positive ion cores, they are quite heavy and they are unable to move about. They are immobile. So the electrons only move around randomly in the solids or in metals. All right. So we are all already familiar, and we already derived in the last lecture that the conductivity is related to the current density as J equals sigma times E. So all vectors, sigma is tensor, the conductivity tensor, and rho is inverse of sigma. All right. So this we learned about in the uh, last lecture. So now we are going to learn how the conductivity or the resistivity, you can say, appears in a metal. So the pioneering work was done by Drude in the year 1900s. So what we are now going to talk about is Drude's theory. All right. So Drude came up with a theory in the 1900s. And most importantly, as I have been repeatedly talking about, that it came from the kinetic theory, basic kinetic theory assumptions, that he invoked kinetic theory. He invoked the principles of the basic kinetic theory. All right. So in kinetic theory of gases, they behaved as hard sphere-like particles. So does the electrons in a metal here. So what happens is that the particle, the box like the box in which the gas molecules were trapped in the kinetic theory of gases, the box here is the metal. The metal body here is the box. So let me just emphasize and write this box in which the gas molecules were trapped in kinetic theory, kinetic theory of gases has translated into a metal body. So let me just write metallic element. It's translated into a metallic sample for the need of explanation of the metallic conductivity. All right, good. So just like the kinetic theory of gases, here also the electrons move about randomly in the metallic sample or the metal we are talking about. All right. So the concept of the gas molecules being trapped in a box is also translated into this Drude picture. All right. So there are some basic assumptions of the Drude's theory. The first one being, which I'm going to write now, is the first assumption. In this model, the mean time interval between two successive collisions is tau. So the typical time scale through which this collision occurs between two successive collisions, the time it takes is tau. And this is the collision time, and we are talking about the collision time of the electrons. The collisions, let's write of the electrons. Collisions of electrons is given by tau. All right. So let me just draw a picture where I can explain clearly. So let's say an electron is there. After a collision, it suffers a collision, it moves here. Again, it suffers a collision and it randomly moves around in the sample. All right. And their motion is completely random. It's not that the electrons are traveling as a whole through a long distance throughout the sample length. It's not like that. They're traversing very short distances and they are suffering a collision. And the mean time interval between two successive collisions is given by tau. And it is the mean time between two collisions. Every time taken by it in two collisions is given by tau. All right. So it moves around randomly in the sample. Now, when we are talking about random collisions and random movements, so we need to know what is the probability that it suffers a collision. All right. The question is, what's the probability? The probability that an electron suffers a collision within time dt is sorry, this is dt. Within time dt is given by simply dt by tau. This is the simple probability. The mean time between two collisions is tau, and your observation time scale, which is dt, which we are talking about. So the probability that an electron suffers a collision is given by dt by tau. And you have to remember, when is this true? As we say, the mean time between two collisions is tau. So before tau, if you're observing before tau, then only you can see a collision. Okay, one collision, you are going to calculate a probability. So dt by tau gives the probability of an electron suffering a collision only when dt is less than tau. Let me just write it with different color. Dt is less than tau. And let me just give you an estimate of tau. Tau is typically of the order of 10 raised to minus 14 seconds. So we are literally looking at very small time scales, and uh, we are talking about the fact that is there a probability of a collision occurring between in this time scale. Okay, and we can easily write that dt by sorry dt by tau equals 1 if dt is greater than tau. It's naturally you can naturally expect that because beyond tau it has suffered so many collisions. If you are looking at, let's say, milliseconds, it has suffered an enormous number of collisions, not only one, it has suffered an enormous number of collisions. So the probability of a collision occurring is definitely one. All right, it is deterministic that it has suffered a collision because we have already specified that within time scale tau the electron is bound to suffer a collision. All right. And an important point to note down is that the electron does not collide with each other. The electrons suffer collisions with the immobile positive ion core. The positive ion cores that are sitting there, which is immobile, which does not move like the electron does. So the electrons are very mobile; they move about randomly, and the electrons suffer collisions with the positive ion cores. All right. And if I have to draw a graph of this probability of collision, and this is et, and this is, let me just write it, probability of collision, uh, probability of collision is dt by tau. All right. So the collision will be given by all right. So this is your 1. This is probability. Of course, it has to be 1. And this is your tau. All right. Because beyond tau, the probability of suffering a collision is 1, as I just explained. So this is the picture of a probability of that an electron suffers a collision, and it is given by dt by tau, the probabilistic approach. All right. And the particles or the electrons are moving around random. All right, it's not that it's traversing a long distance throughout the length of the conductor or the metal, but it is suffering collisions. And if you're observing in a long enough time scale, you are bound to observe new enormous number of collisions. So the second assumption, the second assumption. Second assumption. Between successive collisions of an electron, it can be affected by electric field and magnetic field. Magnetic field. So when the electrons are undergoing a collision, they move about randomly, and in between these collisions, it can be affected by an electric field or a magnetic field. So when you are observing in a time scale which is greater than tau, uh, the before which it has undergone a number of collisions, what do you expect? You expect that it has gone about randomly. All right. So similar to the kinetic theory, here also you expect that the net average momentum of the electrons becomes zero, and the time scale you are observing is greater than time. And when do you see it? As a time scale dt is greater than tau, you are observing at a long enough time scale that it has suffered an enormous number of collisions, so that it has gone about randomly within the metal. All right. So the net average momentum has gone down to zero. So this is very similar. This is very similar to the kinetic theory of gas talked about. All right. So in spite that the electrons are moving about randomly in between two successive collisions, what I said is that electric field and magnetic field can affect on them. All right. So although the motion is random, but electric field and magnetic field will have a role to play in determining their positions, or where they will appear, the electrons where they will appear. The electric field and the magnetic field will be able to determine that. Okay, the trajectory. Okay. So yeah, now comes the third assumption. Okay, third assumption. And if you follow that everything is very, very similar to the kinetic theory of gases, and you realize why I was so much emphasizing on the fact that the kinetic theory of gases is what translates into explaining the conductivity, resistivity in metals. And Drude came up with this excellent, ingenious idea that the kinetic theory of gas can be employed to explain the conductivity of metals. Third assumption is that the electrons, the electron gas are is non-interacting. All right, and this is called your free electron approximation. Free electron approximation. And earlier we also talked about that the gas molecules trapped in a container, they're also non-interacting. There's only kinetic energy between them, and there's no potential energy. So as to say, there's no electron, sorry, there's no electron interaction. Neither do the electrons interact with the immobile positive ion cores. So there's no interaction between the electrons with among themselves also, and with the positive ion cores. At later point, when we go deep into the course, we will see that this interaction with the electrons and the positive ion cores, they are very, very important in explaining some features that will get revealed as we go along deep inside the course. But the catch of the thing is that this simplest assumption, and which is translated from the kinetic theory, is enough to explain very interesting properties and also some of the basic properties of metals in general. We'll see that this simplest theory will suffice to explain basic properties of metals, and this is quite true for large number of metals. So is there any, so this is basically a free electron gas wandering around randomly. They're non-interacting, they're randomly moving about, they do not interact with the ion cores, they do not interact between themselves, and there's a mean time scale tau between two successive collisions, and they suffer number of enormous number of collisions if you look at a time scale which is greater than the mean time scale tau. So this is the basic picture of Drude's theory. All right, these are the basic postulates. What you can say, they're the basic assumptions of Drude's theory. So if we ask a question that is there a experimental signature of this non-interacting, only free electron gas-like nature acting inside the metals? So if we go back to our earlier lecture, we can see, you can recall that we talked about the specific heat of the solid. All right. So at higher temperatures, it was almost constant. This was 3R. All right. As we go along to lower and lower temperatures, the curvature changes and it becomes like CV proportional to T cube. And we said that it comes from the phononic contribution, which is, to remind you, is the lattice contribution. Okay. And as we go down to lower and lower temperatures, we see that the contribution here becomes linear at very low temperatures. Said that and said that it has a linear temperature dependence, and we said that it came from the electronic contribution. All right. So now the matter is, this is a signature of the basic free electron theory of the free electron approximation, where only this is true for large number of metals, that the free electron approximation is valid to explain the basic features at low temperatures for a large number of materials, where the specific heat indicates that it linearly depends on temperature. So non-interacting here means that it has no Coulombic repulsion between electrons. It has no interaction with the positive ion cores. So basically, it is like a free electron gas. So this linear specific the linear dependence on temperature of the specific heat at lower temperatures is an experimental signature to prove that the free electron approximation is valid at for a large number of metals. All right. So let me just wrap up with these three assumptions, which are the basic assumptions of the Drude's model, and we will go on to do mathematics on how the conductivity comes from this, and from probabilistic approximations of the probabilistic approach, we will see that the conductivity that Drude has been successful in explaining the conductivity of metals, and it is a very simple approach which basically came from the kinetic theory of gases, and I have been emphasizing it for almost all the time that this has translated from the basic kinetic theory of gas, where the basic differences are also coming, that in case of solid it is not really constant. The specific heat is not really constant. Sorry, it's constant at high temperature, but it goes down as T cube and later like T at lower temperatures. It is not like a gas. The fundamental differences are also arising, and we will know about this type of differences when we go deep down into the course. So thank you everyone. I think I have wrapped up with the Drude's first basic assumptions, and as we go on to next lectures, we will learn about the mathematics and how the conductivity comes from Drude's approximation. This is a very ingenious model, and it has been successful in explaining many interesting phenomena, or the basic phenomena that people have not been able to explain. So the simplest approach gave the liberty to explain the various properties. All right. Thank you everyone.